Okay, it's 4:45, so I think we can go on with our last talk in the workshop by Benno on incremental analysis in Infer. So yeah, the stage is yours.
Thanks, Akash, and thanks everyone for coming. So my name is Benno. I work at Meta on the Infer team, more or less, and I'm talking today about incremental analysis in Infer. And this is sort of the reaction I always get when I say I'm working on incremental analysis in Infer is, isn't it already incremental? And so this is sort of I'm very excited to give this talk because the answer is, the answer is more complicated than it might seem. And so, in fact, what I'll be talking about today is something a little more like this, that, it works mostly like you probably imagined of the reuse of summaries and compositional analysis. And soon we hope with some developments we've been working on recently and hope to continue pushing on, it'll be even better than that. And so this is a paper that's very famous. It's the original by abduction paper that described Infer, and I think this is sort of one of the main reasons that people think Infer is incremental, and this is a solved problem. And anybody who has worked on incremental analysis has probably had reviewers talking to them that, oh, Infer has already solved that problem. And it's really just this paragraph here on the first page of this by abduction paper. There's a brief aside that says that compositional analysis easily yields an incremental algorithm, which is, more or less true, but not the whole story. So people sort of imagine, they have in their heads that how Infer works is something like this, that you have some source code, you have some invocation of Infer, and that goes into Infer, and then out comes, after some time, some analysis time, you get some alarms, some potential bugs, all the things we know and love from Infer. And then the source code changes, the programmer edits their code, or you pull some changes from a remote repo or something, and then you say some magic invocation like this, some run Infer incrementally, and then out come some new alarms, or no alarms here rather, or if you've fixed them, you get no alarms obviously, or maybe Infer tells you some bugs that you've missed or some new ones that you've introduced. And what we mean for an analysis to be incremental here is that incrementally updating the analysis, it should be both fast and it should be what we call from scratch consistent. So from scratch consistent is a term from the sort of general incremental computation world. It means that when you do a computation incrementally, you should get the same results that you would have gotten had you run that computation from scratch. And so that's a really important property for analysis designers because we want our analyses to be reliable. When a developer is running some batch CI job, they should get the same results as if they're sort of incrementally updating things. This should all be kind of totally transparent from the developer's perspective. It should just be faster and give you the same results. And just, I imagine some people in this room are familiar, but many probably are not, so I'm just to be clear about which parts of Infer we're talking about, what I'm actually talking about here. When you tell Infer to run an analysis, here it's sort of how to read that is Infer run says, run a capture and analysis, and then after the dash dash, you give some build command. Infer hooks into your build command and sort of tries to analyze all the code corresponding to that build. So here it's make, but many different build systems are supported. And the first thing that happens is Infer does what we call capture. It hooks into the build system. It compiles whatever source code. It kind of knows how to understand that build system. You compile your source code into some bag of SIL procedures. So CFGs in our IR, we want sort of a collection of those procedures, and that's the result of a capture phase. After that, we run an analysis phase where you compositionally analyze all of those procedures that you've produced out of capture, and what you get out of that is some table of function summaries, some kind of denotational semantics of the behavior of those procedures. And then finally, after analysis, you have some set of summaries, and you do what we call reporting. So you post-process the summaries, generating some issues, filtering those out, deciding what to report to the error, or what errors to report to the user, etc., things like that. And so capture, I'm not going to be talking about in this talk because each of these front ends, each of these build systems is distinct. Many of them already handle incrementality in their own way. Make famously is incremental. Boris talked earlier today about sort of their efforts on incrementalizing the Ada front end and how to do that. And it's a whole bunch of work, but it's kind of independent for each front end. So I'm going to ignore that here. I'm also going to ignore reporting because it's fast, and we don't really care about incurring that cost multiple times. It's sort of vanishing that cost with respect to both capture and analysis. So For the rest of this talk, when I say infer, when I say analysis, I mean something that looks broadly like this. So the input to the analysis problem is some collection of procedure CFGs in SIL, and the output is some table of summaries. These are called capture.db and analysis.db in infer. I might slip and say that at some point, but basically we're saying procedure CFGs in, procedure summaries out. And when you get a change, we are sort of mocking out all of capture, and so we'll have some new capture database. And the job of the incremental analysis then is to take, given that new capture database, the new CFGs, and whatever summaries it computed in the last iteration, it should update any procedure summaries that are affected by the program edit. And it also has access to a list of the changed files as well. And so, And so, what am I doing? The job of the, that's what I want it to look like. So the job of the incremental analysis is sort of this picture here. And the most basic kind of obvious simple thing that you could do is this kind of scare quotes incremental analysis, where it's not incremental, you can just reanalyze everything from scratch. It's about as simple as you could imagine. It's definitely from scratch consistent because we're just running everything from scratch. And I should be clear that from scratch consistency kind of assumes determinism. Infer analyses are not always deterministic. I'm kind of waving my hands here. The statement we want is something more like we're not introducing any inconsistency of our own, but there is some sort of non-determinism inherent to infer, and we're not solving that necessarily, though there is sort of an orthogonal line of work ongoing to try and do that. Downside, this incremental analysis has zero incremental reuse. And somewhat surprisingly, maybe, this is actually how diff analysis has worked for the bulk of Infer's history at Meta. Diff analysis, I mean when a developer submits some changes to the internal sort of CI system, nothing incremental happens. It's fully done from scratch, and the way that goes is more or less like this, where we first analyze all of the changed files and their transitive dependencies at the diff version, that is with the changes of the developer applied. We generate a report, some alarms, some issues, and then we throw away all the analysis results that we just computed. We check out the parent version, meaning the sort of merge base that they want to apply their changes to, and then we reanalyze everything from scratch, generate another report, and kind of subtract out any alarms from the original report on the diff version that we found also on the parent version, meaning we are only going to report any issues that are newly introduced by these changes. And then we'll issue warnings on that diff for any of those remaining alarms. So once we've masked out what we think are pre-existing issues. And this is sort of surprising to people sometimes, but this is how it's worked for many years, in large part because as deployed internally at Meta, the thing that makes Infer fast is not the incrementality, but the fact that it's kind of on demand. It only analyzes what it needs to analyze in order to analyze the changed files in the diff. And so compared to the size of a monorepo at Facebook scale, the sort of dependency tree of a single diff is small enough that this can be done reasonably well. But it's frustrating, it's inefficient, because we're, for every single change, analyzing everything twice. So every single diff that comes in, Infer essentially does two full analyses of all the dependencies of that diff. And there's a lot of sort of low-hanging fruit in this picture for incrementalization. So sort of one step further than that, the kind of next most obvious thing we could do is just ignoring dependencies. What we can do is just discard any summaries of procedures in the changed files. So we look at the list of changed files that we have from the capture phase. We look at all the summaries we have from the previous run, and we throw away any summaries that are in a changed file, and then we reanalyze. That's great. It gives you lots of incremental reuse. You're going to be able to reuse sort of all of the summaries of callees that are outside of a changed file. But it's not sound, obviously. There's too much incremental reuse. You might be reusing stuff that depends on a changed file whose semantics have changed because you've changed its callees. And this was implemented sort of early on when on-demand analysis was added to Infer, and it's been known as reactive mode, -- reactive, various things. I'm trying not to use sort of Infer-specific flags because those have Infer-specific meaning, and they've changed a bunch over time. But essentially the idea here is with no explicit dependency tracking, you can just unsoundly use all of your out-of-date summaries, and it's probably mostly fine, but not necessarily. And so the sort of diff analysis flow is this first step unchanged. We still do a full analysis of the diff version. And then after generating a report, throw away summaries of any procedures in changed files. After that, you check out the parent version and then reanalyze changed files again. And this will be very fast now because you're only reanalyzing any code in the actually changed files. And then the last two steps are as before. You mask out pre-existing issues and report any newly introduced issues. Yeah, and so sort of one step past that, and this is something that I don't have as much visibility into this because this is well before my time with Infer, but before Infer was a tool at Facebook and Meta, it was a sort of academic tool and then a tool of this startup called Monoidex. And so before their acquisition, they were showing off all of these really cool demos where they would start giving a talk and they would start Infer analyzing OpenSSL. And then halfway through the talk, Infer would finish, it would give them some bug report, and then they would, real quick, on the fly, fix the bug, say incremental analysis, go, and then seconds later get fixed results. And so that's another part of, I think, why there's this kind of folk history that Infer is very incremental. But the way that this worked is that it only tracked static callees. There was no understanding of dynamic callees, of other kinds of dependencies or global state that might crop up during analysis. So you get this very fast incremental reanalysis, but just like the previous iteration that I was just showing, it's unsound with respect to dynamic calls and some other things. And the way it worked actually is that at that time, Infer's analysis scheduler was just make. Infer would look at the source code and it would emit a make file where all of the make targets were invocations of the Infer binary on some source files, and the sort of dependencies within the make file were structured based on the static call graph dependencies that they found in the source code. And so procedure summaries are files on disk produced by these make targets. Each make target invokes an Infer binary. And also each of these targets is at the granularity of what they call clusters of files. So sort of a handful of files that, as far as I know, there is no sort of, they're not a strongly connected component or anything like that. It's just sort of chunks of files that were sort of chunked up that way because of the overhead of invoking lots of binaries. You wanted to sort of throw a bunch of files into the same invocation, and that was how it was efficient to do it. So this was very fast. It meant you could have these very sleek demos, but it was all just based on make files, and it was unsound with respect to both dynamic calls and if the static call structure changed from one program version to the other, everything would be based on the static call structure of the initial program version before there were any edits. And so all of these sort of different versions we've seen, they all sort of, the issue boils down to this sort of key question of how can you actually determine which summaries in practice are affected by the program edits. And so we saw you can just sort of pretend it's only the stuff in the changed files. You can look at the static call structure. What we're doing now instead is a very simple idea. Because the static call graph information misses any of the dynamically discovered callees or ad hoc interprocedural dependencies, what if we just go through and instrument everything? So if we go through and instrument everything, instrument all of our sort of summary application procedures in the analyzer, anywhere where you can look at the type environment from some other file, look at globals, look at global variables, things like that. Just instrument all of that, track all of your dependencies on the fly, and then record that as you go. And that's your kind of dynamic analysis dependency graph. And so that looks something like this. So we can track all of those dependencies on the fly and then record them into our analysis database with the summaries themselves. So every summary now holds with it some information about what else in the program it depended on. And that happens whenever a summary is applied, whenever a type environment is accessed. A couple of other things we've tried to sort of instrument everywhere that we think that interprocedural that analysis data can flow interprocedurally. And so this is great because it gives us some fast incremental reanalysis. It's sound and from scratch consistent with the same asterisk that I was sort of talking about earlier. It's got a relatively coarse granularity, but we think this should at least be kind of correct, sort of match our intuitions of how an incremental analysis should work. And this works as before. So what you'll do first is analyze the whole program, everything you need to analyze, all the changed files and their transitive dependencies at the diff version, generate a report based on that, and then check out the parent version, capture, and discard any summaries that have a transitive dependency on a procedure in a changed file. And crucially, this dependency is in the sense of the kind of analysis dependency graph of any dynamically discovered dependencies you found in the instrumented analysis, not any sort of static approximation of the analysis dependencies. So after you've done that, after you've sort of discarded anything that may have been affected, you'll analyze the changed files and any affected transitive dependencies, so anything that sort of depended on a changed file. And then as before, you sort of generate another report, mask out issues, report them, et cetera. And just to make this a little more concrete, I'll give a sort of brief example here of what this analysis dependency graph actually looks like. And to be clear, file level granularity, that's how we're looking at changes. And so you might have, your program might be a couple source files here, say a.c and b.c. And after capture, you have some database of procedure CFGs. Suppose you have foo and bar in A and F1, F2, F3 in B. You end up with these sort of these serialized control flow graphs for each of those procedures. And then after analysis, suppose you end up with something like this, where you have a summary for each procedure, and then these black arrows denote the dependencies, anywhere that we applied a summary or otherwise kind of accessed data that was not local to the procedure that we were currently analyzing. And you might end up with a graph that looks like this, where say foo calls F1, bar calls F1 and F2, and then F3 is call free. And yeah, I mentioned this already, but these dependencies, this is as best effort. This includes anywhere that a checker uses interprocedural information. And so suppose from this we edited the F2 procedure in B and then tried to reanalyze incrementally. What would happen is basically this, where incremental capture is from the perspective of incremental analysis, from what I'm talking about today, it's mostly opaque. It's handled by the front end. There's some attempts in most of the front ends to do some kind of incrementality, but that's not what I'm here to talk about. And so incremental analysis only knows that the file b.c has changed. And so the first thing it'll do is invalidate any of the procedures of, or any of the summaries of procedures in file b.c. And then it'll kind of transitively walk the analysis dependency graph backwards from those edited procedures and end up invalidating everything in the analysis database. And so in a reanalysis after this, we'll have to reanalyze everything from scratch. And so we can do a little better than this. So I specified that we were talking about file granularity there, which may have given you the idea that we can also do procedure granularity, which is significantly better in some cases. So essentially the same algorithm as before, but we'll check whenever we capture these CFGs, we can check them for structural equality against a previous version. So if we're in the situation where we have a new CFG and an old CFG, we can kind of try and match them up as best as we can, and up to best of our ability, if we can show that they are unchanged, meaning we're ignoring sort of file numbers and source, or file line numbers in source locations or alpha renaming. If the two procedures are structurally identical up to those kind of allowances, then we know that the procedure is unchanged and we don't need to reanalyze it or its dependencies. And so to be clear, this is, if we can know for sure that it's unchanged, we'll mark it as unchanged. Otherwise, we'll assume pessimistically that it could have been changed. And so for the same situation as I was talking about previously for file level granularity, it looks a little bit better here with procedure granularity. So we'll do that structural equality test of the newly captured CFGs and say, since since the F2 procedure in file B is the only thing that has changed, we will sort of know that in our capture database. We've got just a little bit to record that on each procedure CFG. And then we can invalidate only those changed procedures and their transitive dependencies. So in this case, we only end up invalidating F2 and bar, and we can reuse our analysis results for a.foo and b.f1 and b.f3. And so this actually ends up being a pretty big difference in practice. So this is on average across a whole bunch, thousands of meta CI diff analysis jobs. If we do file granularity invalidation, we end up saving around a third of the analysis work at diff analysis. And that doubles with procedure granularity. So if you sort of have that smaller set of roots from which you're invalidating in your dependency graph, you save around 2/3 of the analysis work on average across all the diff analysis jobs in which this is enabled. And this is now what you get in open source Infer. If you say -- incremental analysis, you get essentially what I just described of the procedure granularity and validation and the dynamic dependency tracking. And we've updated the docs on the Infer website, so there should be some relatively sane flow suggested for CI analysis there. And you can obviously also ping me if you have any questions or anything there is confusing. I also want to mention that this 66% is kind of on average across all of our code bases, but in some cases we're finding actually much more effective. For example, in Android analysis, we see at P50 around 75% savings up to like 90% or more at the kind of long tail of P95 analysis costs. So I don't have any sort of solid explanation of why that is, but in certain code bases, certain code structures, this incremental analysis has significantly more benefit than this. Yeah, so this is sort of zooming out. That's kind of the past and present of how incremental analysis has worked and currently works in Infer. But you might have noticed in this picture and in all of those kind of pseudocode kind of steps of diff analysis, there's still a pretty glaring bit of low-hanging fruit. Not low-hanging fruit, but there's still some performance to be clawed back. Because we've made incremental analysis much faster than before, but still every single time we analyze a diff, we do one full analysis, and that's the same as it ever was. So we're saving on this second analysis of the two analyses that compose a diff time CI job, but there's no savings at all in the first analysis. We're still doing a from-scratch analysis of the diff version. And so that probably leads you to think, can we use this incremental infrastructure that we've built up to try and have some savings there as well, to have some inter-diff incrementality where we can kind of memoize analysis results across different diff analysis jobs or other types of analysis runs in different kinds of deployments. And the answer, maybe unsurprisingly, is that yes, we can. And this is work that's sort of ongoing and in progress and planned for the future. Before I explain this, though, I think I'm going to abstract even further out from what the actual analysis is actually doing. And I'm just going to imagine Infer as this, where those capture DB and analysis DB and a bunch of other stuff, that lives in kind of what we call an Infer out directory. And so we'll just pretend that Infer is this black box that operates on some initial Infer out directory, some summaries, some procedure CFGs, whatever you have there. And it does some transformation. It produces some new summaries. We'll just sort of abstract all the way out like this. And then to do this inter-diff incrementality, we need to talk to a couple different other systems. So I'll just sketch those out very briefly. Obviously, we need some kind of version control system to sort of understand which versions are connected to which other versions and how. We're also going to make use of a blob store. So I'll just very opaquely imagine this as some kind of key value store holding zipped Infer out directories that we control the keys of. And we can write and read zipped Infer out directories up there. And then we will also make use of a SQL table, a memoization table that can map hashes of the version control system onto keys into the blob store. So for this version control hash, the results of analysis at that version are stored at this key in the blob store. It's not just the version control hash. You need a little other metadata, stuff like the version of Infer that you're running, the config options that you've passed to Infer, stuff of that sort. But this is kind of the basic picture of what we need in order to kind of reuse analysis results across different diff analysis jobs or in other settings. And the way this will go is broadly as follows. I'll sort of, this is a bird's eye view. I'm happy to talk more details in questions or offline. But the first thing we'll do is look for the closest version control ancestor of the current revision for which there exists some row in the memoization table. So we're sort of going to walk back through the version control history until we find some cache hit, some version for which we have analysis results. We'll grab whatever analysis results we have cached at that version from the blob store. And then starting from that Infer out, we can run an incremental analysis while invalidating anything that's changed since the ancestor version whose results we're starting from. And then once that's done, optionally you can write that resulting Infer out directory back up to the blob store, add a corresponding row to your memoization table, and now those results are available for future reuse by future versions or other analysis jobs. So this is the sort of This is all in place now. There's a lot of work still to be done in terms of integrating this into existing analysis workflows, other kinds of analysis deployments, but we're pretty excited that this can sort of incrementalize Infer further and bring it closer to kind of the image that a lot of people have in their head of Infer as this kind of very sophisticated incremental system that is making really aggressive use of incrementality and caching across different analysis jobs. So I've been talking about this in terms of kind of inter-diff analysis incrementality, but there's a bunch of different applications where this kind of system can be helpful. So first off, yes, inter-diff incrementality. This should help us speed up CI results, get results into developers' hands faster, and also save some capacity in terms of the computation cost of running 2 analyses for every diff job. Similarly, we think this can help avoid the really frequent reanalysis of commonly depended upon but infrequently modified libraries and vendored code, where if you're analyzing a lot of sort of application level code changes in a big monorepo, they probably all depend on some stuff like logging or shared data structure libraries or kind of shared utilities. And so you're probably analyzing those dozens or hundreds of times a day, even though they change at a much, much slower pace than that. And so this is where we think for this kind of system would have some of the most benefit, is kind of saving that reanalysis of these sort of core libraries that are in practice actually quite expensive. They have a lot of kind of complicated low-level code and can be quite expensive to analyze. And we think that saving that will have a pretty big impact on the speed of Infer as deployed at Meta currently. But it can also let us go further than we currently do and enable some diff time analysis of larger targets, so or even larger fractions of existing targets. So stuff like, currently Infer analyzes changed files and anything that is needed to analyze those changes. So all essentially the callees of your changes. But if you're changing some function, you might have introduced a bug in your callers. And currently Infer has no way of reporting on that. Even if the underlying analysis could identify that issue, it never will, because we don't analyze the callers on the diff that changes the procedure. And then anytime in the future we do analyze those callers, that will be seen as a pre-existing bug. So we think there's some fertile ground here for kind of analyzing callers of changes if we can sort of understand better what the dependencies are. And even scaling up to stuff like whole application analysis, where instead of only analyzing the dependencies of the change, if we're able to, using incrementality, get fast enough that we can sort of reliably analyze in reasonable timescales the entire application, then we can maintain sort of global invariance of, there's never any taint flows of this form in the entire application, and we can sort of verify that and report on that to developers in kind of the timeframes that are feasible there. Similarly, this might be able to let us push Infer analysis, sort of shift it left further into the development workflow, stuff like IDE integrations or development time signal at the command line, with a more reasonable user experience and results that are sort of reliably consistent with CI. Because developers won't like this if they sort of run their incremental local analysis and they get some different results, and then they get surprises in CI when the batch CI job runs. So this sort of principled approach to incrementality, we think, can give us kind of faster, more usable results earlier in the development process. Like I've mentioned, this is still ongoing work. There's still a lot of work to be done. So a couple of these sort of key challenges and open questions that are top of my mind are as follows. So first off, how can we balance the kind of recency, that is to say proximity in the version control tree, against trying to maximize overlap of analyzed code? Because as I've alluded to a couple times, at Meta, this is all in the setting of a gigantic monorepo. And so different changes at different points in the version control tree can touch wildly different parts of that monorepo. And so you want to sort of memo match onto analysis results that not only are as recent as possible, but also have kind of maximal overlap with the changes that you're analyzing at that diff. And so how to key your memo table such that you get kind of maximal reuse, not only maximal recency, is to us an open question. And part of how we address that is sort of targeting analysis of these libraries and vendored code that is heavily depended upon but infrequently changed, because the hypothesis being there that many different code changes in different parts of the monorepo have a sort of common set of shared dependencies, and if we can memoize those, then that will be a lot of savings. And similarly, it's not clear how we can kind of represent and compare different uncommitted changes at the same version control revision. So if we're doing IDE-based analysis or development time analysis in the terminal, this is just going to be on the current version of code in the developer's working copy. And so reasoning about the relations between different versions there is non-trivial, especially if a developer is, changing, analyzing. We want to kind of have that maximal reuse across all those different versions, and it's not obvious how to do that using the current infrastructure. And lastly, we would love to make as much of this as possible available to open source users, because a lot of what I've sketched out here in terms of the blob store and the SQL and all of that, that depends on Meta internal infrastructure, but the kind of underlying idea is something that we think could be broadly applicable to other industrial and academic users of Infer. And so making these APIs as sort of generic and usable as possible for external users is something we'd really like to do going forward. We are, for example, very happy to see Buck2, which is a recent Meta open source project that is a build system that's all totally generic in the remote execution and sort of blob store and content addressable storage infrastructure that it uses, that at Meta is all internal infrastructure, but they've sort of defined APIs for it such that it's pluggable with other different systems for similar infrastructure in the outside world. And so we would love to follow that lead and make Infer as usable as possible and make these incremental features as available as possible to external users. So that's all I have. I'll thank you for your time and be happy to take any questions.
Yeah, thank you for the talk. So there's already one question on Discord by Boris. Which comparison do you use to detect that procedures are identical after the second capture? Asking because we tried that and got hit by functions being considered different just because of, for example, line numbers after the beginning of the file changed.
I can share a code pointer. If he greps for mark if unchanged snake case, he will find it. I can find the code pointer and send that to him.
Yeah, you can also pop it in Discord or whatever.
Yeah.
Okay.
It's a very naive thing, as I described. It just sort of takes the two CFGs, tries to walk them in parallel, builds up a kind of mapping so that it's resilient to alpha renaming, and then compares the parts of the IR that we care about. So it ignores stuff like line numbers. And that is code that has been used for various purposes across Infer for many years and has been kind of resurrected and whipped into shape recently for use here. But it is kind of well tested and
okay, then maybe what Boris and his team was trying was an older version where this didn't work as well.
Yeah, it had been kind of allowed to drift and bit rot a little bit as different Infer IR changed underneath it. But it is now, I am pretty sure, working as expected. And as I mentioned also, it's pessimistic. It will either show, yes, these two things are definitely identical, or throw up its hands and say, I'm not sure.
Okay. Thank you. Any questions from the room? Yep.
Yeah, so I had a couple of questions. So this, your SQL table, it's located, is it located locally in the monorepo, or it's located in the Meta's?
Sorry, which piece is located?
Your SQL table, the blob store.
Yeah, so the blob store is a Meta internal system that we lean on for this. I believe it's called Manifold. It's been talked about publicly in some of these sort of discussions of Buck2. The SQL table, the schema should be in public stuff, but the table itself is in Meta distributed MySQL infrastructure that.
So if you want to run it for the local builds, that's not possible, right?
Yes. So I think currently. Oh, sorry. Yes. Oh, that's very loud. Currently, for open source users, I think of what I've talked about, the thing that is available is kind of everything before I split off and started talking about that infrastructure. That lives in kind of code that needs to integrate with Meta internal infrastructure and systems, and so that is not part of the OCaml infer repo that is sort of synced with open source. That's all written in Rust, that all kind of operates in a different world. Open question, future work to sort of try and bring as much of that infrastructure into the open source part of Infer as possible. But right now what's available is kind of this -- incremental analysis flag, which will kind of, it's for a single infer invocation, reuse as much as you can of the existing infer out to compute the infer out of the target that's been specified. Yeah.
And when you computed this overall performance benefit, that was in terms of analysis work, like 33% analysis work. What does that mean exactly?
Runtime.
Runtime, okay.
Yeah.
Okay, thank you.
Thank you for the nice talk. Quick question. Have you looked at what characterizes those commits where your incremental analysis is able to save a lot of effort versus those where it cannot?
No, is the short answer. This is deployed across a ton of code that I don't understand, and so it's very hard for me to kind of jump into some random bit of code and understand that. I think I could make hypotheses, but
okay.
I would have not much confidence in them.
Okay.
Yeah.
So we do whole program analysis and we do this incrementally, and there for us it seems to be modifications to like globals in some sense. But I'm not sure if this would transfer to an analysis that is more modular right away. So
yeah, I think that would make a lot of sense to me. That would definitely be something I would think about, right? Because one thing I didn't talk about in a lot of detail is the way this instrumentation works, that if all of your changes are just in source code in a procedure, then the only ways those will propagate and the only sort of edges we'll get in the dynamic dependency graph are applications of that summary. Mm-hmm. But if you change the value of a field or you mess with some type declarations in a file, then we kind of conservatively fall back to kind of the whole file level granularity. And so globals and stuff like that will have a much bigger impact than any source code changes that are sort of isolated to a single procedure.
all right, thanks. And the second question, if I may? Sure. So you said you're only reporting the diff in the warnings, right?
Correct, yes.
So have you thought about maybe giving up from scratch consistency if you only care about the diff anyway? And
yeah, so I think from scratch consistency is important for a couple reasons, not only for this kind of masking out of pre-existing alarms, but also for kind of reliability from our perspective, that Infer is a team of plus or minus a dozen people working on it, and they're sort of often tasked with diving into debugging, figuring out what happened here, and minimizing the sort of sources of inconsistency and sort of making things as understandable and reproducible as possible is sort of, to me, that's the main benefit of the from scratch consistency, is sort of the reproducibility and reliability of results. Not necessarily the sort of, preserving some kind of soundness or some like meta property of the analysis itself like that, because Infer is already not sound. And so we're sort of focusing here on reproducibility and reliability and kind of usability for developers and engineers working on Infer and having their code analyzed by Infer. So that's the motivation for kind of the from scratch consistency-ish stuff here.
all right, thanks.
Mm-hmm.
Nice talk, Ben. As you are going from whole program to file level to function level, your analysis is going to come up with more and more false negatives. Is that, did you observe that, and what your experience with this is? Are you losing out on more and more analysis results or bugs that you were finding earlier in the whole program scenario? You're not finding them anymore. So what was your experience, and how did developers view this?
So do you mean in terms of when we're invalidating analysis
Exactly.
results at a finer and finer granularity?
Yeah, are you losing out a lot of context, right, in that sense? But depends on how precisely you're computing this,
Right.
and what you're missing out on.
So from my perspective, if there are changes in the analysis results, that's a bug. That's an issue that I need to fix. So how we invalidate and where we invalidate and how much we invalidate should affect how much work happens in the next analysis run, but it should not affect what the analysis results are. We should get the same results either way, up to the other sources of inconsistency and non-determinism in infer. So I don't think we should have different characteristics of false alarms, false positives, false negatives than we would have without the incrementality. There have been a couple bugs. You know, it's a gigantic, messy code base with everything connected to everything. So I'm not confident that this is true in 100% of cases, but it's sort of the broad strokes, the way the system is designed. I don't think it should have significant effects on the precision, the quality of the alarms that come out of the tool.
That's good to know. So yeah, basically, did you compare thoroughly with what whole program analysis does versus the incrementality? And is this in practice that you observe, or is this in theory that,
Right. So in practice, yes, but sort of proof by example, right? It's there's infer runs many, many times, dozens, hundreds of times a day, and so I can't sort of shadow everything and make sure everything runs twice and then automatically compare the results. But especially in the early days when we were deploying this and I was rolling this out, I was doing a lot of kind of manual comparison. Oh, we got some alarms in the incremental thing. Let me make sure that we get the same results if I manually run a non-incremental job under the same configuration, and vice versa. And we've had a couple bugs of like where we do have issues introduced by incrementality, but those have all been fixed quickly. And so at this point, I'm quite confident that that it's not introducing issues of that sort.
Yeah, that's good to know. The other aspect is that you're also storing a lot of information there, right, in your DB, right? So
Indeed.
From a company perspective, so you're storing a lot of data summaries in your database, and then you're comparing against it, right? So you think that's like the right trade-off, and it's still a good investment?
Yeah. So of course I'll make a distinction here between the sort of within one diff job incrementality and then the kind of caching results for reuse across different deployments in this blob store. For the former, I don't think there's any trade-off at all. I think so long as we can, our constraint is really, can everything fit in memory? Like, if everything can fit in memory, then we're fine. It's all savings. For the setting where we're sort of storing stuff in this blob store, there is a trade-off to be made there, and sort of we're not going to be storing the results of every single infer analysis in perpetuity, and so there's some tuning to be done in terms of like time to live, as well as kind of deciding which runs get to populate that cache. I think storage is relatively cheap compared to compute, where we feel much more crunch on, using a lot of servers. An infer job is very expensive. It'll sort of max out a big server in terms of memory and compute pretty quickly. Compared to that, the amount of data that we're storing is relatively small, but it's not free, obviously. I'm not an expert on this stuff in sort of the large scale, but it's, these artifacts that we're caching are on the order of a couple tens of gigabytes at most.
Okay, that's not much. Okay.
So it's not a
And the
crazy-
code base size is roughly, is it 10 million, or is it?
Sorry, the entire
size of
mono
the-
repo.
Yeah,
Oh, I don't know the answer to that.
okay.
Do any other meta people know the
That's
answer to
fine.
that? Yeah.
Maybe.
I know that, for example, the WhatsApp server is like 5 million lines of
5 million, okay.
That's relatively small compared to like hack and everything, so I would imagine like hundreds of millions, but yeah.
I would hazard a guess at on the order of hundreds of millions. Yeah.
Okay. Okay, thanks.
Thank you. So in the meantime, there was also a question by Radu on Discord, but maybe you have already kind of answered it. Yes, Radu says that it's mostly answered. His question was, if I understand correctly, the problem with the -- incremental -- analysis was that it was unsound, but now it should be. How sure we are that it is, but I think you touched this. And the follow-up is, if we change something in Infer, when should we pay attention to update the instrumentation that records dependencies?
So that's actually a great question. We've tried very hard, and this is all in the public Infer OCaml repo. We've tried very hard to wrap things, the sort of obvious interfaces by which you would, say, apply a summary or access a type environment, wrap that stuff in code that does the instrumentation such that analyses don't need to think about this at all. That's the goal. Before I started all of this work, there was a ton of kind of ad hoc interprocedural stuff, right? It's applying a summary is one thing, great, but there's a lot of places in analyses just because they're not thinking about incrementality where they would say, look at some metadata about the callee, and then based on what they see in the callee at some call site, do one thing or another thing, right? Just sort of that kind of ad hoc use of information from outside of the procedure being analyzed. Very common, very normal. And so we sort of did a lot of kind of searching through all these different checkers because Infer is home to dozens of checkers. No one person understands every single one of them. And so the goal was to sort of looking at all of those, sort of targeting, obvious culprits and then going out from there and trying to find as many of these interfaces as we could, wrap them in instrumentation code that all sort of goes to a shared, I think, relatively clean and neat interface for tracking these dependencies. All of that is context. I think my sort of straightforward answer to Radu's question would be, if you're doing something that within a checker is trying to access some information about another procedure, if it doesn't go through sort of the obvious blessed interfaces, which maybe we should do a better job of annotating this in some way, but our goal is for it to basically be transparent, and any way that this is possible to do should be wrapped in some kind of instrumentation code. I'm not positive that that is the case. The code will change in the future, and when it does, new surfaces might be introduced that are not wrapped in this, but in the current status of things, I think it should be impossible to access this information without going through one of these instrumented code paths.
Okay, thank you. I think this should again mostly answer the question, and again, you can probably discuss further offline. So yeah, thank you again.